Everybody can see the, hello?
Yes.
Yes.
All right, so you can see the presentation?
Yes.
Great. Should I start or?
Please.
All right, thank you. All right, thanks, Dr. Ali, for organizing this nice webinar today. My presentation will be about a paper that's recently published in the Transportation Research Record journal with the title of Genetic Algorithm-Based Approach for Roadside Units Deployment in Connected Vehicle and Automated Vehicle Environments. This research was done as part of my dissertation work under the supervision of Dr. Sharif Ishaq. So the outline for my presentation today, I'll start with some introduction about the subject matter, and then motivation of my research and objectives. And then I'll discuss a mathematical model that's called ConRAP, or Connectivity Robustness Model, that I'm using as the basis for my approach, and then the methodology, and then I'll talk about the simulation modeling and the results and discussion, and we'll end up with the research findings. So a transportation network in connected and automated vehicle environment would have two primary components, and this is the futuristic goal that we're looking into having. So we will be having only the vehicles and the roadside units, nothing else. So to manage such network at the traffic management centers, we'll be dealing with the two main components that we are always dealing with in travel information systems, which is the data collection. We'll be collecting data from the vehicles and processing this data and then disseminating information back to the vehicles, and this will be all done through the roadside units. So to guarantee a successful management process here, we need to have robust and stable communication between the vehicles and each other, and between the vehicles and the infrastructure. The challenge, however, here will be that we may not have enough vehicles in the network that will help us have this kind of stable communication, especially at the early deployment of the technology. However, or nonetheless, we can try to maximize the benefit from the resources that we have, from the number of vehicles that we have in the network, by optimizing the locations of the roadside units such that we're able to communicate with as many vehicles as possible and collect the most representative data that can be obtained from such network with such conditions. Having said so, the objectives of or the objective of my research was to optimize the roadside units and locations with the objective function of maximizing the communication stability and robustness in the network. And by doing so, as I said, we're able to communicate with as many vehicles as possible in the network. But the question here, how can we quantify or measure the communication stability? This will be using the ConRAP mathematical model, or the connectivity robustness mathematical model that I developed as part also of my dissertation research. It's based on how vehicles are clustered in the network. So for instance, if you look at the image here to the right, given a specific market penetration in this network, we might have vehicles clustered as we see here. So we have two clusters, which means that the vehicles in one cluster can communicate with each other easily, but a vehicle from one cluster is not able to reach the other vehicles in the other clusters. Of course, the best case scenario for these two clusters is for them to get close to each other and merge into one larger cluster of vehicles that's covering a larger area of the network. So here we wanted to, we looked at these clusters, and we wanted to quantify how stable the communication, or how the vehicles in one cluster can maintain the communication that they have, and wanted also to quantify the potential of the different clusters to merge with each other into one larger cluster. So we used the analogy, we looked at these two clusters as two masses, and we used the analogy that is in Newton's law of universal gravitation. As we all know, it measures the attraction force between two objects using the law that we all know here. So we said that similarly, we can say that instead of the attraction force, we have something called connectivity, robustness, and stability, or the potential of the clusters to merge and their ability to maintain the communication that they already have. And it equals some constant C multiplied by a surrogate measure for the first cluster M, multiplied by a surrogate measure for the second cluster M, and this is divided by the square distance between the two clusters. So there is a very long derivation for this model that can be found in the paper that I just mentioned, that is published in the Transportation Research Policy. I'm not sure if I did say this, but anyway, the final form of the model is a time-dependent connectivity robustness, because vehicles are moving all the time in the vehicle, in the network. So the connectivity robustness between cluster N and M equals to the reciprocal of the number of clusters in the network at this time t, and of course, the fewer the number of clusters, the more robust the communication would be, because this means that we have more vehicles communicating with each other in the same clusters. This is multiplied by the mass of the first cluster, which is LRN T. This is some measure for how far are the vehicles, or how the vehicles are distributed within one cluster. This is divided by the minimum transformation range within that cluster. This is multiplied by the square root for the number of connected vehicles in that cluster, divided by the total number of connected vehicles in the network. This is all multiplied by the square root of the area covered by this cluster at time t, divided by the total area of the network. Same thing applies to the second cluster, and this is all divided by the square distance, or the square of the minimum distance between the two clusters, and this is normalized by the transmission range of the vehicles plus 1. So this is the measure that we are using as a performance measure to evaluate the communication stability and robustness in the network. With that, what we're trying to do again is to develop some optimization algorithm for roadside units deployment by maximizing the network connectivity robustness, and we used genetic algorithm as our main tool here. So if we look at the image again that I just showed, these two clusters, we're trying to find the location for the roadside units where we can link them together into one larger cluster, as we all can see here. So this slide shows the way genetic algorithm work and how we mapped our problem to that. So we start with a population of n chromosomes, or a number of chromosomes. Each chromosome is formed of an n number of genes. Then for that population, we apply some fitness function, and we to identify the fittest chromosomes for which we do crossover and mutation for them to reproduce new chromosomes, or new generations of chromosomes that form another population or a new population, and the process keeps going on until the fitness of the chromosomes does not improve any further. So the way we map this to our problem, a gene was represented as a roadside unit. A chromosome is an arrangement of n number of roadside units, or we call it a deployment plan. The search space in which we're trying to locate or deploy our roadside units is all the intersections and access points in the network, and these are the potential locations where we can deploy the roadside units. And the population is a p number of roadside units arrangements, or p number of deployment plans. And most importantly here is the fitness function as we said in the connectivity robustness model, the fewer the number of clusters, the more robust the communication would be. So our fitness function here was the total number of clusters that a roadside unit deployment plan was able to merge together and maintain merged over time. When the time, of course, relies on our study period. So to test our approach, we extracted a vehicle trajectory data from a VSIM simulation model for around 200 square miles road network that is located in Washington County in Oregon, Portland. For these trajectories, we applied 32 scenarios with 4 different market penetrations, 5%, 15, 25, and 50, and 4 roadside unit deployment scenarios, 42, 58, 68, and 100. And we compared between a uniform deployment and optimized. The uniform means that the roadside units are just equally spaced in the network without any optimization. But the optimized is what we obtain using our approach. We used an effective transmission range, or assumed an effective transmission range of 1,000 feet. And for each scenario, to evaluate the performance of the roadside units deployment plan, we calculated our performance metric, which is the connectivity robustness. So this slide right here shows the fitness function on the performance of our model. As you see here, the fitness on the vertical axis improves or increases for the different deployment or different number of roadside units as the number of iterations in the genetic algorithm increases, until we reach a state where the fitness function does not improve any further, which means that we reached an optimal solution. So to evaluate the performance, we are going to look first on the number of clusters, the final number of clusters we have in the network after deploying the roadside units. And this is here for the different market penetration scenarios. If we look at the 5%, for instance, we will find that with the uniform deployment, which is presented in the gray lines, the number of clusters decreases as the number of roadside units increases, which is very logic, because we're mainly adding some stationary vehicles, more like stationary vehicles. So we're kind of increasing the market penetration a little bit, which helps the vehicles or the vehicle clusters to merge with each other. But when we deploy these roadside units optimally, we find the optimized locations or the optimal locations, we can improve that performance by reducing the number of clusters in the network more significantly. Same thing applies for the 15 and the 25 and 50% market penetration. For the connectivity robustness, which is our main performance measure, we also find here, if we look at the 5% market penetration, that as the number of roadside units increases, the connectivity robustness increases as well, meaning that we are reaching a more stable communication between the vehicles just by using the uniform. But if we move from the uniform to the optimized, we can benefit more by that and achieve higher increase in the connectivity robustness. Same thing applies for the different market penetrations as we see here. So with that, I can say that our approach was able to deploy the roadside units at locations where we can communicate with as many vehicles as possible, where we can connect and link as many vehicles as possible for the same market penetration, which is the main objective why we applied that approach. Of course, adding roadside units in the network, even with the uniform deployment, leads to an increase in the connectivity robustness. And as I said, it's because of we're more like adding stationary vehicles. But when we move from the uniform deployment to the uniform to the optimal deployment, we can achieve more gain in the connectivity robustness. The final finding here is that our network level connectivity robustness performance metric tool can be used as a planning tool for such applications, like the one that's of interest in this study. And this is one of the objectives, or the main objectives, why we developed this model in the first place. I mean, the network level connectivity robustness model. So to summarize and wrap up what I did here in this study, if you look at this image for the network, given a specific market penetration, vehicles can be clustered as we see here. We're only looking at the connected and automated vehicles. We're not looking at the entire traffic, or all the traffic in the network. So we wanted to say, or to collect data from this network, or to be able to manage this network, we can deploy the roadside units equally spaced or uniformly, as we can see here. By doing this, we can link 2 clusters here and 2 clusters right here. So we're able to communicate with these clusters. We covered more area, and this means that we achieved higher, we increased the connectivity robustness, communication stability in the network. But if we deploy these roadside units optimally using the genetic algorithm approach or the proposed approach, we can reach a state like this. We may reach a state like this. And this is an ideal state where all the connected vehicles are reachable in the network, and we're covering a significant area of the network area. I'm leaving this roadside unit right here, which has nothing to do, or is doing nothing, not communicating with anything, to show how can this work improved in the, as a future research. All we did here is just optimally deploy the roadside units, or find the optimal locations for the roadside units. But in addition to that, we can also try to find the optimal number of roadside units. So for a roadside unit like this one, we can simply remove it because we know that it's not adding much, or it's not doing much. So we can achieve a cost-effective approach here, in addition to it being optimal. So these are the 2 papers that I like. The first one is the main study that I was discussing today, and the second one is the paper that shows the derivation, or the connectivity robustness model that I used as a performance metric here. So with that, I conclude my presentation, and I'm ready to take questions.
Thank you, Dr. Osman. Any questions from our audience?
Hi, Dr. Osman. That's a very interesting presentation. My name is Han Wei. I have several questions. I'm very interested in this research. And so in your research, you simulated the connected vehicle and autonomous vehicle. Are you split those 2 different type of vehicle, or combine them together?
I'm actually combining them. I'm not splitting them.
Okay. So regarding the connected vehicle, so do you consider in the business simulation when the functions switch between connected and fully automation?
All right. So yeah, to answer this question, I need to go back to this slide right here. Mm-hmm. So what I did basically is that I ran the simulation for 1 hour and extracted the vehicle trajectories, and assigning the connected vehicles and connected automated vehicles based on the market penetrations that I have here was done all in MATLAB. So all I did was randomly find assign the connected and automated vehicles according to this percentage in the vehicle trajectories that I have. So I didn't have to simulate how those types of vehicles work in the simulation environment, but I did that in a separate study.
Okay, so In the connected vehicle, actually, because you have, you know, the 32 scenarios and including the full market penetration and the 5%, 50%, 25%, that means there are also the rest of the vehicles are not connected or non-automated vehicle. Is correct?
Yeah, that is correct. Yes.
Yeah, yeah. So have you, in your simulation, have you considered either any interaction between the connected or automated vehicle and the non-CAV, whether that either any impact between them, and also this impact, I believe, somewhat even sometimes significant on the performance in overall.
Actually, didn't get to that the interaction between the vehicles. So all I did is I took snapshots for the vehicle trajectories every specific time step, 10 or 100 seconds, as far as I remember.
Okay.
And for each snapshot, like it's kind of like static snapshot, and I try to see where the vehicles are located, and based on that, I deploy the roadside units.
Okay, so I just provide information because my advisor, a PhD student, he just graduated. Right now, he's working at the UC Berkeley PATH program. His dissertation focuses on how the behavior interaction and impact on the performance. So we may in the future find some time or TRB we can meet to share something. So that's very interesting because he has got a lot of new findings because of the behavior, the impact between, you know, the CAV and the non-CAV, that it really, you know, mean the impact on some of the scenario. So your study actually focused on the largest scale of network than our study, but we focus on different aspects. But if we put together, that will be perfect.
Sure, that would be a pleasure.
Yeah, and also another question regarding, you mentioned that optimization of the roadside unit. Could you give for us the details or the example, what kind of the roadside unit and the functionality?
I didn't get also into that detail in my research because all I'm dealing with to find the locations is nodes that have some transmission range, like the one that I'm assuming here. And based on these nodes, the locations, I'm trying to allocate these nodes and deploy in the locations of these nodes until I achieve a higher benefit or a higher connectivity robustness value. So I didn't get, my research didn't need this kind of high level detail of the functionalities of either the vehicles or the roadside units.
Okay, so do you have any the vision function like in your mind, and that maybe work as if you know, the detector from the third part or communicate with the vehicle? So what the primary functions do you have in your mind?
I'm sorry, maybe I didn't get the question right.
Oh, what I mean that the roadside the unit, what the function, if we have, you know, or whatever deployed in the field, what is the function you expect? That means
for the roadside units.
Yes.
You mean collecting data and disseminating information?
Yeah. That's what I'm curiously, what the primary function that's supposed to have.
Okay, so this is all going to be working based on the SAE protocol, the J2735, the communication protocol that's used as the basis for the connected vehicles. So what happens actually is that vehicles, as they move, they collect data, they collect snapshots of data. Each snapshot had maybe the locations and the speeds, and those snapshots are collected every maybe 0.1 second or 1 second, depending on what type of messages we are in or like are being collected, either the basic safety messages or probe data messages, or there are several types of messages that can be collected. And as the vehicles fall in the transmission range of the roadside units, they simply kind of send all these messages that are stored on the onboard unit of the vehicle to it, and then from the roadside unit it goes to the traffic management center, or maybe analyzed in site to develop some useful information that can be disseminated back to the vehicles also when they pass by the roadside unit location.
Okay, so I noted that actually focus on the range of the transmission range. Actually, that is DSRC, right? 1,000 feet. Yeah. Okay. So have you considered any 5G or any other potential? That may be.
No.
Okay.
No, I didn't get into that. Yeah.
Okay. Yeah. I have a last question. Sorry for taking so long time.
Sure.
And did you consider the impact of the traffic control at intersection? Or
you mean in the network itself?
Yes, because based on our test, intersection, at least the existing intersection, the needed to, be changed a lot because it doesn't fit to the connected vehicle system.
All right. So in this network, all the intersections that you can see here in this image are signalized intersections. But as far as the impact of that, I didn't get into analyzing it. As I said, all I'm interested in is getting some snapshots and finding the locations of the vehicles within that snapshot. So it's more like static, but over time. Like I go one snapshot at a time and then keep going until I see one roadside deployment that can maintain the higher number of clusters merged over these across these snapshots.
Yeah.
I didn't get into the studying the
okay.
analyzing.
Yeah, I raise this question because in a scenario, we consider we definitely it's not the possible to switch our system to from 0 to 100% of the connected vehicles. So maybe gradually with the different percentage of penetration, just like you propose in a scenario. So that still during the transition, some the existing signals still impact on the connected vehicle and the connected vehicle. So that is maybe still the issue. Yeah. I really appreciate it. Thank you very much. That's all my question.
Thank you.
Well, thank you, Dr. Wei. These were very interesting questions. I was very interested to hear your discussion.
Thank you for your organization, so that we have a chance to share, the idea.
Yeah,
that's great.
And so I do have one more question. Actually, I have two questions. So now the clusters, were they defined solely on the distance between the cars during the simulation?
Yes, they are based on the distance between the cars. Yeah.
Which is the 1,000 feet.
Yes, exactly.
Okay. Now my question is on an observation I have, or a question I have on slide number 11.
Yep.
So a higher connectivity robustness is that better or lower?
Higher is better.
Okay, because.
Yeah. All right. So this might be confusing. I agree with. All right. So the scale of the vertical axes here are different. So the first one, the 5%, is 10 to the power 10, and the 15 is 10 to the power 8. The 25, 10 to the power 7, and 50 is 10 to the power 4. So the 50 is still higher than the 25. 25 is higher than the 15. The 15 is higher than the 5. If that's what you mean.
Yeah, I think I think this helps. So, but still isn't the power 10 higher than the power 8? Or is this 1 over?
I'm sorry?
Is it multiplied 10 to the negative 10 or 10 to the power 10?
No, to the power 10, not to the negative 10.
So, which isn't a value multiplied by 10 to the 10 higher than a value multiplied by 10 to the 8?
I'm sorry, this is negative. I'm sorry. Yeah, this is negative. Yeah.
Oh.
Yeah, sorry, this is a typo here. Yeah, so sorry about that. Yeah.
Oh, no worries.
Yeah.
All right, so this is, as Dr. Wei pointed out, this is extremely interesting.
Thank you so much.
I have a couple of my students also working on impacts of SAVs and connected vehicles, but in a GIS platform.
Awesome.
So maybe we can all get together and.
Yeah, that would be great.
Yes, I agree. We may form a team
Yeah,
for future study.
why not?
So, Ali, are you going to TRB, attend TRB?
Yes.
Okay, so how about we set up, the time we meet together?
Sure. I think that would be very beneficial. Too bad.
We may attend, the committee meeting, right?
Yes, I think Dr. Osman is also planning to attend, right, Dr.?
Yeah, I'm coming.
Yeah. So we may, meet, just for a short conversation. We may, in future, we may, join to collaborate and prepare the proposal or something, or publish a paper,
Sure, that would be awesome. Yeah.
Yeah. All right, great.
Any last questions from any of the audience? Well, I want to thank our presenters today, Dr. Wei and Dr. Osman, again for two very interesting presentations, followed by even more interesting discussions. And I want to wish you all a great, happy holiday season. And I hope I will see you all at the TRB meeting and our ABJ70 committee meeting. And with that, I think we have reached the end of our webinars and the end of today. So I want to thank you all again. Wish you a great day.